Hi everyone. The last lesson we have already discussed about the derived quantities as well as derived units. Today we are going to deal with the dimensions of physical quantity. As you already know, all the derived quantities can be expressed in terms of 7 fundamental quantities. And the dimensions of these 7 fundamental quantities, we can say that 7 dimensions of the world. 7 dimensions of the world. So which are the 7 dimensions of the world? Or which are the 7 dimensions? As you already know, you can see how to represent the dimension. The representation of dimension is in square bracket. So the first one, length, we used to represent capital letter L in square bracket. Same way, mass, capital letter M in square bracket. Time, capital letter T in square bracket. Temperature, capital letter K, or sometimes can be used the theta in square bracket. Electric current, that is capital letter A or capital letter I in square bracket. Luminous intensity, CD in square bracket. Amount of substance, which we represent the dimensions in square bracket, mole. So these are the 7 basic quantities as well as their dimensions. So once again, what is meant by dimensions of a physical quantity? Dimensions of a physical quantity are the powers to which the fundamental quantities to be raised to represent that quantity completely. So that is the definition. You can see the definition here. Now let's discuss few examples how to write the dimensional formula. Alright, so let's discuss few examples for dimensional formula as well as dimensional equation. So first one, let's discuss about the first one, that is area. As you already know, area is length into breadth. So I'm writing once again, length into breadth. What is the derived unit? Meter into meter, that is equal to meter square. So here, instead of that derived unit, we can use the dimension. So what is the dimension? Length dimension is capital letter L in square bracket. What is a breadth dimension? That is also capital letter L in square bracket. So what is the answer here? You can write the answer as in square bracket L square. In square bracket L square. So this is the area. Now let's discuss the second one. That is density, volume density. As you already know, density is equal to mass by volume. If you write the derived unit, we can write the kilogram divided by meter cube. So if you are writing the dimensions for mass, that is capital letter M in square bracket, of course, divided by what is a meter cube? That is a unit, right? So what is the dimensions of that one? We can write the L cube. So what is the dimensions of density here? We can write the M L to the power L cube. If you take it into numerator, it becomes M L to the power minus 3. M L to the power minus 3. Now let's the third case here. That is velocity as well as speed. So I can write here velocity. What is the velocity formula? Velocity is equal to displacement by time. What is that? Displacement divided by time taken. Derived unit is meter divided by second. If you write the dimensions, we can write the for displacement is L, time is capital letter T. So what is the dimensions? We can write here L T to the power minus 1 in square bracket. L T to the power minus 1. Clear? Now let's one more example, fourth one as force. As you already know, force is equal to mass into acceleration. If you write the dimension formula, if you write the derived unit, you can write the kilogram acceleration m s to the power minus 2. If you write the dimensions of this one, mass we used to represent capital letter m. Meter is a length, no? So we can write the capital letter L. S, that is a time unit. So what is the dimension? Capital letter T. S to the power minus 2. So we can write there what? T to the power minus 2. So this is the dimensions of force. Now let's discuss the other case here. After force, we can consider here work done. Let's see what is the work. What is the work formula? Force into displacement, right? So we can write the force into displacement. Force into displacement. F into S is equal to, force is what? Kilogram meter s to the power minus 2 into displacement. Once again meter, right? So we can write here what? Kilogram meter square s to the power minus 2. So how to write the dimensions of that? So we can write the dimension as mass m meter square. For meter square we can write the L square. S is in time in second, so we can write the dimensions is capital letter T raised to minus 2. So we can write the here minus 2. So this is the way to write what? Dimensional formula. Now let's discuss about another example, as that is stress. You can see here stress formula. What is meant by stress is equal to? Stress is equal to, once again we say that force divided by area, same as the pressure. So tangential force divided by area it is. Force by area. So we can write here force is what? Kilogram meter s to the power minus 2 divided by area is meter square. So what is the dimensions here, or what is the derived unit here? Kilogram meter raised to minus 2 plus 1. So minus 1 s to the power minus 2. So this is the derived unit. So what is the dimension formula here? Instead of kilogram, mass capital letter M, length L to the power minus 1, second time quantity raised to minus 2. So this is the way to write the dimensions of stress. Correct? Let's discuss one more example, that is the strain. S-T-R-A-I-N, strain. Strain formula. Strain formula is change in length divided by original length. Delta L represents what? Change in length divided by original length. If you write the unit here, delta L is in meter, length is in meter, meter cancel, so there is no unit. So we can say that there is no dimension. There is no dimensions for this strain. So some physical quantity will have dimensions, some physical quantity won't have the dimensions. So it is again divided. So we'll discuss this one now. Now let's discuss about different types of variables and constants. So variables are mainly divided into two. One is dimensional variable and other one is dimensionless variable. And constants are also divided into two. One is dimensional constant and other one is dimensionless constant. So let's discuss about one by one. First one is dimensional variable. Dimensional variable. The physical quantities which is having dimensions. Physical quantity which is having dimensions and the values, the magnitude are variable. The magnitudes are variable values, and that is called what? Dimensional variable. What are the example for that? Any example you can take it. Area. Area, what is a unit? Meter square. What is the dimensions? L square. So which is having dimensions and the value may change, right? maybe area is 10, 20, 30, whatever it is, 30 meters square, etc. So that is called what? Dimensional variable. So once again, example, area, volume, velocity, acceleration, etc. Next one is called what? Dimensionless variable. That means which is not having dimensions, but the values, magnitude may change. So what is meant by dimensionless variable? The physical quantities which doesn't have any dimensions, but the values, magnitude may what? Vary. So you can see the definitions here. Example, angle. What is angle formula? Arc length divided by radius. Length divided by radius, meter by meter, length L by L. So there is no dimension, it will cancel. But even though the value may change, 10 degree, 30 degree, 40 degree, etc. So this is called what? Dimensionless variable. There is no dimension, but the values are varying. So another example we have discussed just before, strain. Strain, there is no unit. Change in length by original length. There is no unit. There is no dimension, but the value may change. So that is called what? Dimensionless variable. Now let's discuss about the third one is dimensional constant. Dimensional constant. The physical quantity which possess dimensions and their values are constant. And that is called what? Dimensional constant. Example, gravitational constant. It is having unit or it is having dimensions and the values are what? A constant value. Planck's constant is having dimensions or having unit. The value is what? A constant. Okay. Next one is dimensionless constant. Dimensionless constant, which is having no dimensions, but the value is a constant value. For example, if you take pi, 22 by 7 or 3.14, it's a constant value. Is there any dimension? There is no dimension. Pi value, there is no dimensions. This is an example for what? Dimensionless constant. Now let's discuss about the application of this dimensional analysis or dimensional formula. What are the applications we are using here? So you can see the first application. What is the first application here? It is used to check the correctness of given relation. What is the first application? To check the correctness of the given relation. Second one, derive the relationship between the physical quantities. It is used to derive physical quantities relationship or relationship between two or maybe many physical quantities. And the third one is the dimensional analysis is used to convert one system of unit into other system of unit. So what is the third one? To convert one system of unit to other system of unit. So these are the mainly three applications we are using. So now let's discuss about the application in detail. Alright. So the first one is that. What is the first one? To check the correctness of given relation. To check the correctness of given, or the question may come like this. Prove the principle of homogeneity. Prove the principle of homogeneity. So we are now going to discuss the first application in this class. What is the first application? To check the given relation is correct or not. Now let's discuss one question here. One equation we can check it here. F is equal to mv square divided by r. mv square divided by r. Maybe some students know this equation or maybe someone don't know this equation. Leave it. I will tell what is the each letter represents. You can write it down now. F is the force. Note it down. M is the mass. V is the velocity or speed. R is the radius. R is the radius. F is equal to mv square by r. What is the question? Prove the principle of homogeneity or to check this correctness of this given relation. We are going to check whether this equation is correct or not. So how to prove this equation is correct or not by using or by the application of dimensional analysis. So this is a way to prove it. First case, dimensions of, you can note it down, dimensions on LHS, dimensions on LHS is equal to dimensions on RHS. This is what we are going to prove it. So what is the LHS means? Talking about the force. What is a force dimension? Force is equal to mass into acceleration. So we already discussed that one. LHS dimension is m L t to the power minus 2. So we have proved LHS is equal to mass into acceleration, force it is. Now we are going to prove the RHS, right hand side. First one is mass. What is the dimension of mass? Capital letter M in square bracket. We can put it together in square bracket. Velocity is what? Velocity dimension is L t to the power minus 1. L t to the power minus 1. That is, velocity is what? Meter per second. So L t to the power minus 1. But we are using here mv square. So put one square here. Divide by, next one, divide by what? Radius. Radius dimension is once again what? So you can put it in square bracket. Radius is once again what? Length, right? So capital letter L. Now you can open this bracket. M, that is only one M is the, if inside the bracket, square bracket, L t to the power minus 1 all square it is. So how to use this one? If it is coming in powers, multiply the powers here. So first one is L to the power 1. L is L to the power 1. So 1 into 2. So what is 1 into 2? L square. Next one, t to the power minus 1 all square. So you just multiply this number, minus 1 into 2. So we can write here t to the power minus 2. Divide by L. Divide by L. That means you can write here m L square t to the power minus 2 into, if you take the denominator into numerator, it becomes what? L to the power minus 1. So that is equal to m L square L to the power minus 1. So what should be done here? If the same quantity is coming, the same dimension is coming there, add the powers. So 2 plus minus 1, which is equal to what? 1. So m L. Once again, only one time is the, so t to the power minus 2. So put it in the square bracket. Now check the LHS and RHS. LHS is m L t to the power minus 2. RHS is also m L t to the power minus 2. So what we have proved here, LHS is equal to RHS. So what we can say here, the given equation is dimensionally correct. Or we can say that we have proved here principle of homogeneity. Principle of homogeneity. I hope it is clear. Let's discuss one more example. Okay, one more example. See, this is the one. V is equal to U plus A into T. So maybe definitely you know this equation, even though I will say here, V is the final velocity, U is the initial velocity, A is the acceleration, and T is the time. How to prove that the given equation is correct or not? How to prove it? So once again, dimensions on LHS is equal to dimensions on RHS. So what is the dimensions on LHS? LHS dimensions, we can write here, V is the velocity. So we can write the L t to the power minus 1 meter per second it is, right? But you see the right side, there are two terms are there. One is U and other one is AT. So if there is two terms are there, what is the meaning? V is velocity. So that means you are adding two quantities also must be velocity, then only you will get the answer, right? You cannot add one physical quantity with another physical quantity. That is different dimensions, right? So this is V. So this is also dimensions will be same as this V. And this is also dimensions is same as V. So what we are proving here, dimensions of V must be equal to dimensions of, I'm just not writing here, dimensions of U. Same way, dimensions of V must be equal to dimensions of AT. So let's prove this one. First one we have proved, dimensions of velocity is equal to dimensions of U. U is also velocity, initial velocity and final velocity. So these are dimensions are same, Lt to the power minus 1, and here which is equal to Lt to the power minus 1. Now next one is V equal to AT, right? So dimensions of V is equal to what? Lt to the power minus 1. Now next one, which is equal to, what is the dimensions of acceleration? That is meter per second square, right? ms to the power minus 2. So dimensions Lt to the power minus 2 into time is what? Capital letter T. Dimensions capital letter T. So what is equation become? L, this is minus 2 plus 1. That is equal to Lt to the power minus 1. So what we have proved here? This equation is also dimensionally correct. Dimensionally correct. Okay. One more example. See the equation I am writing here. Kinetic energy is equal to 1 by 3 mv square. Definitely you know this equation is not correct. But even though we will write down this one. Just imagine you don't know this equation. Your equation is given, the energy is equal to 1 by 3 mv square. Now we are going to apply the dimensional analysis. What do you have to prove here? LHS is equal to RHS. LHS is equal to RHS means what? Dimensions on LHS is equal to dimensions of RHS. Okay. LHS is energy, right? Energy means what? Work done. Work done is what? Kilogram meter square s to the power minus 2. So LHS dimensions is ml square t to the power minus 2. Now let's prove the dimensions on RHS. So this is the LHS. Now we are going to prove here RHS. What is RHS dimensions? 1 by 3. That's a constant, dimensionless constant. We don't bother about that one while you are dealing with the dimensional analysis. Next physical quantity is what? Mass. Mass means capital letter M. We use to represent the dimensions. Once again, velocity. Velocity m into velocity square. Velocity is L t to the power minus 1 whole square. This is equal to what? M into L to the power 1 into 2. L square, right? Into t to the power minus 1 into 2. Minus 2. So you see this LHS and RHS. LHS is equal to RHS. That means the dimensions on LHS is equal to dimensions on RHS. So what we have proved here? Principle of homogeneity, or we can say that the given relation is dimensionally correct. The given relation is dimensionally correct. But you see this equation. This is not actually correct equation. What is actual kinetic energy formula? Half mv square, no? So this is the drawback of this dimensional analysis application. What is the drawback? You cannot find out this constant. Okay, we can only check the correctness of the given relation by using dimensional formula, but the constant we don't know how to calculate using dimensional analysis. So this is the one of the drawback of dimensional analysis. Okay, so you cannot calculate the constant value, so you can only check what the physical quantity dimensions are equal on LHS and RHS. Okay, I hope it is clear for you. Now in the next lesson we will deal with the other application. Okay, so you go through the many questions like this and just answer the dimensional equation, dimensional formulas, and check whether the given relation is correct or not. Okay, thank you all of you.